Hello, good afternoon. How is everyone feeling after lunch? Sounds a bit sleepy. Woof. Tough crowd. So I have the great pleasure of introducing Macklin Hartley. And Macklin's been incredibly awesome with DDD, helping us to solve a huge amount of issues on the front of our website as well, accessibility issues as well. And in fact, this is actually one of the talks that I voted for as well. So yeah, go DDD. Anyway, without further ado, hand you over to Macklin.
Thanks, Rob. Good afternoon, everyone. How great was lunch, by the way? It was fantastic, wasn't it? It was delicious. I'm actually hoping you're all in a bit of a food coma, so you don't notice any of my mistakes if I make them. So, it's great to see so many people here to hear me ranting about my talk. Every good outage starts with a queue. So let's get us started. First off, what exactly is a queue? Well, you might remember queues from various normal day-to-day activities such as climbing Mount Everest, or that one time your engineering lead got stuck in the train and he was late for work. Or maybe that one super interesting and riveting data structures unit that you had in university. How queues work is actually pretty simple. It's a bit like the Mount Everest queue example. The first person in the queue actually gets to see the top of the mountain first. And subsequent items in that queue join at the end, and they have to wait until they can be moved to the front of the queue before they can get dequeued at the end. It is really quite simple. I'm going to be talking specifically about messaging queues, which are specifically for distributed messaging systems. So maybe I could get a little bit of a hands up. Who's used distributed messaging before? So something like Amazon SQS, for example, or Azure Service Bus, RabbitMQ, or perhaps you're like us, we actually rolled our own because it was fairly simple for us. So I saw a lot of hands up. That gives me the impression that I think developers actually quite like queues. They're quite keen on them. But why exactly is that? I can think of a couple of reasons, right? So first of all, they offer just a really simple logical separation. So the idea is the message publisher, the person who publishes the message into the queue, they don't have to really understand how the downstream processes are going to be doing their job, or in fact, how many of those downstream processes there are. So that's kind of nice. On top of that, they can act like a bit of a shock absorber. So they can iron out the effects of getting a whole lot of traffic all at once. And that will ultimately make your system much more responsive. Lastly, and this is more important for us, they offer this unique kind of persistence mechanism. So we store all our messages indefinitely in the queues that we build, and that will allow us to, later on, we could reprocess that data to gain new insights and get new information out of that. So I'm going to talk a little bit now about the system that I've been working on lately that does use queues. So what we have here to begin with is there was a third-party system, and they were sending messages onto consumers, various internal systems that we also have. None of this is our stuff. What we wanted to introduce in the middle was a message proxy that could listen to these messages, maybe store them, and maybe later on we could process that information later on to gain insights from, like I described before. In this example here, our consumers have turned into the tenants of this message proxy system. So the problem here is if we do this naively, and the message proxy receives a message from this external third party, what happens if we fail to send that message on to our tenant? So that we could just drop that message on the floor, but then the tenant would never receive that data, and that's a potential loss of data, which is not really what we want. I guess the other thing we could do here is stop and wait a little bit and retry and hope that it works. But what happens if that tenant is down for like 5 minutes? We can't keep this request open for 5 minutes. That's just not going to work either. So what we decided to do was introduce a queue. Now, the queue is the orange thing in the middle. And what happens now is the message from the third-party system is received, and we immediately store it, and we can return a response straight away. After that, a process manager is picking up these messages off the top of the queue, one by one, and it will send that message on to our tenant. The great thing here is if that tenant is down, and we fail to send that message, we can just wait and retry without keeping requests open because the process manager is in a different process. So it's worth noting here that we were very confident about this system. I'm actually, the diagrams I had here represent a very small amount of the system. We had actually tons of process managers. I was just trying to keep it simple. But we were quite confident that we'd built something that was resilient and would scale pretty well. And we were very close to learning that at this point that we were actually probably a little bit cocky, is the way I describe it. We built a system, but we'd done it quite naively. And I'm about to go into some lessons that we've learnt in that process. So the first lesson we learnt was that observability and monitoring are absolutely essential if you're building any sort of distributed system. So many monitoring tools these days are actually fantastic. Without much configuration, they can tell us lots of details about the web layer. They come with default configurations usually for the web layer, and they can tell us stuff like our average response time, how many errors we're getting, and this thing called AppSec scores, which I don't fully understand, but that's in there as well. However, when we set up our monitoring, because these tools were configured to their defaults, we actually neglected to think about the metrics that were directly related to the performance of these queues. One that we found was actually particularly important, at least for us, was a metric called queue depth. So queue depth is basically the number of messages behind in the queue your process managers are compared to the top of the queue. So as you can see here, we were finding that we were recording occasional very large spikes in our queue depth. At its peak there, it's about 8,000 or just under. But that was never to the detriment of our response times. Whenever queue depth rises, it takes a long time for messages to be received because our queues have to actually catch up, and that causes delays. This actually for us represented an outage of over 40 minutes, which was not a great outcome. So the second lesson we learned was that it's important to learn and understand the true throughput of your system. Throughput was actually a really big issue for us in general. And going back to the system that we were working on, we identified that only some of the messages that we were receiving, even though they all looked the same, some of them were important enough that they needed to be delivered as soon as possible, and the rest, there was never any detriment to any delay in sending those messages. So what we did to combat that was we chose to put these messages into two different queues, and they'd have two different process managers that could process them in concurrently. But now we have twice as many queues. That should mean we fixed our queue depth issues, right? We've turned this into a concurrent process. We can have two processes firing twice as many messages to our tenant. It's faster now, right? Well, probably not, unfortunately. So it pays to think about queues a bit like leaky buckets. The bucket gets filled from the top with messages, and it can get filled very quickly. And then messages are drained out the bottom through the small hole that you can see there. It's possible to fill this bucket up much quicker than the bucket is actually draining out. Our queues were able to ingest roughly 2,000 messages per minute, but we found out later through measuring this stuff that our messages per minute going out, the messages that we were able to produce was only roughly 500. This is what, this caused the buckets to fill up very quickly. And it's important to think, maybe you can think of queue depth, for example, as how full this bucket is at any given time. So deciding to put in a second queue, a high priority queue and a low priority queue, was actually a bit like adding a second bucket. So now we can process 1,000 messages per minute. Great, that's fantastic. but we can also ingest twice as many as we could before. So we'd not actually solved any problem here. Not to mention, nothing was really guaranteeing us at this point that we wouldn't fill one bucket exclusively. So nothing was stopping us from receiving a high volume of load of these high priority messages and just having the same problem that we started with. So measuring the limits of our queues was actually very, very valuable to us. We learned that adding more queues didn't necessarily equate to more throughput, unfortunately. We'd actually solved our problem at least for 99% of the time. The high priority queue is working for us well. But unfortunately, it was never going to be enough to protect us from a high load. So onto the last lesson that we learned, and that is understanding how the external factors of the system can impact your throughput. So going back to how our process managers worked, what they did is they would dequeue one message at a time, and they would forward that message on to our tenant. That was actually through HTTP. We measured how long that entire process took, and we learnt that it was about 150 to 200 milliseconds. Doing a bit of calculation, based on that number, we can calculate that it should be able to process around 500 messages per minute. And that was actually more than enough for our general load. We did load testing to confirm this, but most of the time, that was perfectly fine for us. But what would happen if our tenants, their response time significantly increased? What if the response time actually jumped up to somewhere between 2 and 5 seconds? It sounds oddly specific because this is something that actually happened to us, exactly this. So when we recalculate with this in mind, we actually have a message rate that significantly drops to only about 30 messages per minute. The response time was actually also fairly erratic, so it was often jumping up to more than 5 seconds. That made the calculations much less reliable as well. 30 messages per minute was never going to be enough to cover our general load as well, so that was not good. So why exactly does this happen? Well, one big reason is because our system is using sequential queues. So the only way to get sequential messages one after the other, to our mind, was to to send those messages through sequential queues, to perform those messages one after the other. Something that I've been thinking about for a while is that trying to do this sequential queuing is probably a little bit naive. Putting such a restriction around these queues made them easier for us to conceptualize and validate and test, and it was a lot clearer. And there's a lot of value in that in terms of building a distributed system, because that system is already really complex. Like I said before, we had lots of these process managers, and it was all very complicated. So it was nice that these were easy to visualize. But ultimately, that limitation alone caused us all sorts of headaches for throughput. What it really means is the only way to think about beginning to fix this is to start thinking about how we could process these messages concurrently. So we tried a few things. First thing we did was batching. So this is similar to what we had before. We were still going to be sending one request after the other, but instead of that request containing one message, why wouldn't it contain 100 messages? Then we could send stuff a lot faster. Unfortunately, something weird happened here. It turns out the response time at the tenant increased the larger number of messages that we sent, and that was just something that was out of our control. It was up to the implementation on the other side. And ultimately, this had zero effect on the throughput, obviously. So we were still sending roughly 50 messages per minute. And honestly, the response time was about 50 seconds, so that was never going to work in the real world. The next thing we tried is something that we came up with. We came up with a name for it. I don't know if there is a name for this, but we called it fan out. And ultimately, this is similar, again, to what we have in our current process. There's just one process, but the idea is that we'll fan out to multiple threads and try to send those messages concurrently, if it could. It would then wait for all of those messages to be sent, before continuing on. And if any of them failed, it would be able to retry. The result there was actually pretty good. It was a lot faster. We were looking at roughly 4,000 messages per minute. Another implementation that we haven't had a lot of chance to look at yet is sharding. So going back to that bucket analogy, sharding is a bit like adding lots and lots of buckets. But the difference here is that we can guarantee that an even distribution of messages will land in each one of those buckets. We're hoping, we're still experimenting with this, but we're hoping that this is faster still, just because this will be leveraging will be scaled out to lots of process managers, and we'll be leveraging that compute a lot better. So what did we learn today? Well, it's important to think about how you'll observe and monitor your queues. Think about the metrics in particular that are directly related to queue performance, such as queue depth. Understand the throughput and the load limitations of your systems. Make sure you get accurate measurements and understand the maximum throughput of your process managers and queues. And think about queues a bit like leaky buckets, if that helps. And lastly, learn the behavior of your external systems and make sure you understand how that has an effect on your queues. So don't make assumptions about how your external dependencies will behave. Maybe measure and try to understand what happens if that behavior does change, because ultimately it did to us. So queues are often a great tool, and they have many, many usages, but and as well, often they're the perfect solution to a particular problem as well. But it's really important to understand that they have their limitations. I think queues are a really powerful tool, but they're only powerful when they're used thoughtfully, and if they're used naively, they can cause you all sorts of issues. So that's it for me. I've actually finished a little bit early, but that's fine. I'd like to thank the team at DDDPerth. I think this is actually truly a great conference, a fantastic community, everything. I've actually attended for a number of years, and it's actually a really awesome privilege to be able to speak at this one. I'm really, really stoked about that. I'm going to do a little plug because I've got the time now, I guess. I work for, let's see if I can get this. I work for these guys here, VGW. It's a great place to work if you want to have lots of opportunities to learn from amazing senior developers. And if you're interested in tackling problems like this, like large scale, and using the latest technologies, I work with Kubernetes day to day, which is fantastic, and we use all sorts of other cutting edge stuff. You can meet the team. They're running the coffee cart sort of down the back on the opposite end of the theatre, or you can have a chat with me after. So yeah, that's it from me. I'm not taking questions because, well, I say here there's not enough time, but yeah, there's not enough time. I'm not taking questions. But you can reach out to me on Twitter if you like, or you can catch me at the coffee cart. I might wait around there after there if you want to talk to me, or if you're coming to the after party, just come and say hi. Thank you very much.